Hello everyone, my name is Vishwa Mohan and I welcome you again to this YT video on data structures and JavaScript. We have been following this playlist where I intend to cover the entire data structures and algorithm which is needed to crack any big company as such using the JavaScript stack. Now DSA I am doing right now in JavaScript, but it's language agnostic, so you can still follow if you want to do it in any other programming language of your choice. Do let me know how this series is going on. Your comments, your share, your little love really motivates me a lot to bring more such content. If your love continues, if the channel keeps on growing, I am planning to bring a detailed 2 months long system design course, well planned, well organized, everything free for you on this YouTube channel. So just so a little love, support, share with your friend circle and make sure that our community is growing. And now let's get started in this YouTube video where we go and talk about how do we find the time complexity of a recursive function. In the last video we understood the foundations of the recursion, that how it is function being called inside the function. Here we'll go a little deep dive and understand that how the time complexity, how the algorithmic analysis of a recursive functions are done. When it's about iterative, it's much simple and straight, but in recursion you need to apply a little more brain. It's very interesting and we'll see that how do we do it in this video. So now let's get started, right? So on the screen you see there's a recursive function which is present, right? So if you see here, this is my factorial function and then I've written the code which is a recursive code. Now at this point, I want to go and find the time complexity of this function. If you try to revise quickly in the previous videos, the first session that we did, we defined what the time complexity is. What is the definition of the time complexity? The time complexity was how the number of operations is proportional to the input size. Right? In the case of iterative function, the function where there is an iteration, that is equals to the number of times the loop execution count. It means that if the loop runs for n time, number of operations is n, loop runs for n square time, number of operations is n square. So in the case of the iterative one, I go and find with the help of how many times the loop has been executed. Now in the case of the recursive function, if I have to go and find the same answer, that dude, how many times the operation has happened proportional to the input size, what I can say that it should be proportional, typically, that how many times the function is called, how many times function is called recursively, right? In the case if it is a recursion, and I know the time complexity definition is what? How the number of operations is proportional to the input size. Number of operations in the case of iterative where you have loops is equals to how many times the loop has run. In the recursion there is no loop, but there is a function calling another function. So can I go and say that the number of operations here will indicate that how many times the functions are called one inside the another, and how is that depending on the input size will help me identify the time complexity. So basically if I have to go and find the time complexity of this factorial functions, what will I have to do? I'll have to go and find how many times function is called recursively. So in order to achieve this, in order to know that how many times the function is called, we go and create something called as a recursion tree. And using the recursion tree, we are able to identify that what will be the time complexity of this. Fair enough? So let's try to see that how do we go and find the recursive tree of this. Let me copy this and let's try to move in the next page. So let's say this is the code. Now if I see here, if I look here, the time that will take to execute this line of the code, right, this will be constant time it will take. And then here if you see here, it is getting multiplied with this, right? So here again this section could be the constant and this is the recursive call. So if I go and try to represent this in the form of a recursive function, this might look something like this. T of n is equals to T of n minus 1 plus some constant. Can I go and say this? If I have to go and find the recursive relationship, I can go and say that Tn is equals to T of n minus 1 plus c. Can I go and represent it like this? Fair? So now if I go and create the recursive tree at the level 1, I go and create something like c comma T of n minus 1. So now since I have this recursion formula, right, this recursive formula which you see here, Tn equals to Tn minus 1 plus c, let's try to go and build the recursive tree here, correct? So what I do now is, let me go and clean this up. So at the very first time, like let's say only one is running, then first the constant time this operation happened, and then perfect. And now if I go and expand this cycle at the next level, right, how it will look like? C, and this thing, if I want to go and expand this will become C T n minus 1 n minus 2. If I go and further try to expand it further, it might look something like C, 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 and it will go eventually T n minus n, right? Something like this goes like. So the number of operation here will be what? The number of operation here will be the height of this tree, And how many times this C has happened is equals to the height of the tree, which will be equals to NC. So number of operations proportional to the n times C. C is a constant, right? So the time complexity here will be order of n. So this is the recurrence function, right, time complexity order of n that we have identified. Let's try to understand this further with the help of another example. So let's say this is the example which is there on the screen. Now here if I go and look around and try to find the recurrence relationship, this will take the constant time. And here this is the recursive function again, which is happening 2 times. Fair? Does it make sense? Okay. So what that means is that for a given C, right, if I go and see that T of n is equals to 2 times T of n minus 1 plus some constant, right? This is the recurrence relationship which I have. What that means that if I have to go and break this up, I can go and say that C, and then C has T n minus 1 and then T n minus 2, right? This is how I can go and represent this. If I go and break down further, this is the first layer. The second layer, it would look something like C, and then inside this will be again C, again this will be C, and this will be T n minus 2, T n minus 2, this will be T n minus 2, this will be again T n minus 2. If I try to go and repeat this cycle again, this will look like C, then C, then C. And then typically if I have to go and expand this one, right, so here it becomes C, right, and this becomes equals to T n minus 3, T n minus 3, and then here again it becomes T n minus 3, this becomes T n minus 3, and then here becomes C, T n minus 3, T n minus 3, and this will be C here again, T n minus 3, and this will be T n minus 3. So if you see here at the first level, there is 1C, here it has 2C, here it has 3C, right? And we'll keep on going like this. It will go for how many times? It will go for n times. So total count C plus 2C plus 4C plus 8C, and like this it is going, right? So if I go and take the C out, it becomes 2, 4, 8, 16, like this. If you can see, this is a geometric progression, If I go and find the sum of this value will be equals to 2. The common ratio here will be 2 to the power n minus 1, 2 minus 1. How I dedicate it? This is a geometric progression, right? This is a geometric progression. Whose first term is 1 and the common ratio is 2. So this is the value that I go and get it, right? So if I see here, my number of operation is proportional to 2 to the power n. So the time complexity will be equals to order of 2 to the power n. Am I clear? So the time complexity of this question is order of 2 to the power n. How did we find it? Let me go and quickly revise it again. See, in this function, if I go and see here, let me go and define this function once again, so that if you have not understood, you can get it again. So I have found the time complexity will be equals to this function 2nt minus 1 plus v. Why? Because this is a constant time that it is taking, and then I am again calling this function recursively here again. Now if I have to go and expand this, I can go and say that when this is written, I can go and say the constant, and then it is calling 2 times 2 tn minus 1 tn minus 2 tn minus 1 itself, right? And then if I go and further recursively expand this will become equals to c tn minus 2 tn minus 2. This will become c tn minus 2 tn minus 2. If I go and further down, this thing will recursively get broken down into this form. So the total count that comes here is c plus 2c plus 4c plus 8c, right? So it becomes c 1 plus 2 plus 4 plus 8, 16. It's basically a geometric progression, and this is how I go and find time complexity is order of 2n. If you're finding it intimidating, just pause it now, go back, watch this video, and then move forward. Let's take few more examples so that it becomes crystal clear for you people. Okay, let's get started. For example, in this case, right, this is a binary search code which we'll go and learn later, but let's try to see the code here right now. If you go and see the code here right now, typically this will take the constant time. This should also take constant time because I'm not doing much here, right? And basically this is where I'm calling things recursively. I'm calling things recursively. So either I'm going here or I'm going here, either or. Either this will be called or this will be called, but any of the times if you see here, initially my binary function was called from left to right, but now here it is called from the left to the mid, or from here it is called from the mid to the right. So basically when it is a recursive call, input size is getting halved. So the whole this code, if I have to go and find in the form of a recursive function, I can go and say that tn becomes half plus c. That's how it is. And based on this, if I start building the recursive, how does it look like? So basically I can go and define this portion, right, in the beginning. So it will take some constant time and then followed by tn by 2. This is the first time. If I do the second level, then it becomes c, and this further will be broken into c tn by 4. So if I go and continue the trend, typically how the tree will look like, the tree will look something like this: c, 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 and divided by some term, right? It almost vanishes, right, typically. So how many times, if you go and see that, every time the t value is getting incremented, right? What will be the height of this tree? So if you remember your time complexity session, every time when the size gets halved, it is pointing towards a sequence of what? It is pointing to the sequence of, if I go and tell you that something is n, then it is becoming n by 2, then it becomes n by 4, then it is becoming n by 8, and we did that in the term of the time complexity session. This is representing the logarithmic of n. Here also if I go and see, it is becoming, it is n by 2, that is becoming n by 4. So finally when it all vanishes, right, how many times do you think the c would have come down? What will the height of this tree? This will be equals to the logarithmic of n. This will be of logarithmic of n. So the number of operations here will be what? It will be c log of n. The time complexity here will be order of logarithmic And so this is how I go and find the time complexity of this binary search. Let's move further and try to solve the next problem to understand this better. If I go and see this problem again, this will take me what? A constant time. Fair. And now here I am trying to find the mid. So this will also take the constant time. Then I am calling this function recursively. This is again a function called as recursively. And now if you see the last part, right, this is the mergeSort algorithm. I have not written the other part of it. Assume that this has the time complexity of order of n. It takes linear time, right? So typically how much time it will take? It will take n times constant. So if I have to go and represent this recursive function of this, it might look something like t of n equals to t of n divided by 2, right? And it is 2 times plus n times c, right? This is the recursive formula that I have. And using this, if I go and start creating the recursive tree, then typically what happens in the beginning, I have nc, and for that I have t n by 2, and then I have t n by 2. And if I try to go and expand it to the next level, then it becomes nc followed by n by 2c, n by 2c. Fair. And then here it becomes t n by 4, t n by 4, and this becomes t n by 4, and this becomes t n by 4. Fair enough. If I take one layer further, this might look something like this: nc followed by nc by 2, nc by 2, this followed by nc by 4, nc by 4, nc by 4, nc by 4, and then this lower will have t n by 8, 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 t n by 8. Can you see this? This is the tree which is getting formulated, and this is up to the layer. This is the layer up to layer 1, this is layer 2, this is layer 3. If I keep on moving, it will keep on happening like this. If you see here at this layer, I have nc. At this layer also, if I go and add all of them, it is also nc. At this layer also I have nc itself, right? So each layer I have nc. Now how many times, if you see here, how many times, so what will be the height of this tree? If you see here, it is the size n, then it is becoming n by 2, then it is becoming n by 4, and then it is becoming n by 8. So every time it is getting half. So I have to go and find how many times this will happen. This will be equals to log n times. Now at each level, it is nc, and it is happening for log n times. So total number of operations will be equals to nc times, that should be equals to nc times log n, right? But c is a constant, right? I can also go and see n log n. So what will be the time complexity? I'll take this portion, and the time complexity of this will come out to be time complexity is equals to order of n log n. So this recursion tree is a beautiful concept. I want you guys to master this. It might be a little intimidating in the beginning. Just pause the video, watch it multiple times till you master it. Do a little practice, and then you will get a hang of it. Fair enough. Let's try to see, move on and try to understand another question. This is a custom recurrence, right? And what it is here, if I go and try to see here, it will be a constant time, fair. Then I have, this is a recursive function where the size get reduced by 2. There's another recurrence where the size goes by the 4, right? So if I have to go and define this recursive function, I can go and say that t of n is equals to t n by 2 plus t n by 4 plus c. This might look like this. Fair? Let's say to build the same tree, in the beginning it will be c and first constant time that it takes, and then it is t n by 2, and then it takes t n by 4, right? Then the next level, if I go and try to build this, this becomes C, and then it becomes C, and then it becomes T n by 4, and then T n by 8. Right? Think of expanding this portion. N by 2 has to be half, n by 4, n by 2 by 4 is n by 8. And similarly here, if I go and do this, this becomes C T n by 8 T n by 16. Right? Can you see here? Fair? Now if I keep on, now if you see here, it's slightly different from the previous problems. If I go and see the previous problems, all of them are divided by the same number. Now, as you can see here in the previous case, all of them was n by 8. What it means that in the previous case, when I had created the tree on the left and the right, the size was same. But here eventually if I go and expand it further, right, it will form something like this, from this will go deeper and this will stop here itself. Why? Because at one right hand side it is getting divided by 4 and the left hand side is divided by 2 itself. So the rate at which it is getting half is much smaller than the rate at which it is getting half, right? So this is how the tree will form, right? So here in this case we have to do some kind of approximation. We have to do some kind of approximation. So what we'll have to do is that we assume that this also goes till here and we have to find the same sequence. So if you see here at first level I have 1C, at the second level I have 2C. Similarly at the third level, if I go and expand this, will be 4C, right? So it will be like C plus 2C plus 4C and the sequence will go on. And how many times it will happen? So I'll go and take the maximum time that it can happen, right? So it is becoming n by 2, n by 4, every time it's becoming half. So it is going to happen for the log n times, right? So if I go and take all these things common, so this becomes C 1 plus 2 plus 4 dot log n times. This is a logarithmic progression, so this becomes C into A is first term, 2 is the common ratio with 2 to the power log n base 2 minus 1, 2 minus 1, which is equals to C times 2 log n base 2. Now if you see here, if 2 to the power log n base 2, this will turn out to be Cn itself, right, where n is linearly proportional. So this time complexity here will be equals to order of n. The time complexity here will turn out to be order of n. Fair enough. Again, a very good question. I want you people to again give it a try and understand what is happening here. Let's try to move on further. Now in this question, if I try to follow the same approach, this will gonna take the constant time, this is gonna take the constant time, and my recurrence relationship will be Tn equals to Tn minus 1 plus Tn minus 2 plus some constant time, right? And if I try to build the tree, this looks something like this: C Tn minus 1, Tn minus 2, fair? And if I go to the second level, this becomes equals to C, and then this becomes C, and this becomes Tn minus 2, Tn minus 3, and this becomes Tn minus 3, this becomes Tn minus 4. Fair? If I further extend this, this becomes equals to C, constant, and this becomes equals to Tn minus 3, Tn minus 4, fair, and this becomes equals to Tn minus 4, Tn minus 5, this becomes equals to Tn minus 4, Tn minus 5, this becomes Tn minus 5, this becomes equals to Tn minus 6. Again, if you see here, this is going down at a slower rate, this is going down at a higher rate. So typically when the tree will be formed, typically this will be higher and this will be smaller. But then again, as we did in the last case, when we don't have all of them going down with the same rate, we do the approximation. So ultimately, finally, if I have to go and see that what will be the final recursion tree of this might look something like this. So this finally should look something like this. It is C. At first level I have 1C. then I have 2c, then I have 4c, and it goes for n times, so it becomes 1. So if I have to go and write this looks something like this: c plus 2c plus 4c plus 8c, and it will go for n times. Fair enough? So if I have to go and do this, I can take the 1 plus 2 plus 4 plus 8, and it happens for n times. It's a geometric progression, right? So I can go and say that c into 1 into 2 to the power n minus 1 by 2, right? So it's approximately equal to the power n to the power c. So the time complexity here will be what? This 2 to the power n part. So the time complexity here is order of 2 to the power n. Fair enough? So with this we have come to the end of this session. I understand that this is going to be a little intimidating for you people. So what you have to do, if you feel that you are still confused, re-watch the video. Take out your pen and paper, take the question, write the question in your copy, build this recursion tree and try to solve this problem and see if everything is all fine. Fair enough? Great. So we'll keep on learning this journey. We'll continue this data structures and algorithm in JavaScript. Keep savoring your love. Put that into the comments if you find it helpful. Thank you.